Now we come to one of the more difficult aspects of ionic compounds, but it is crucial for our understanding, and that is naming. We must be able to name ionic compounds, recognize ionic compounds from their name, and provide that information as communication to others. If we can't name ionic compounds, we will be severely limited in our ability to communicate. So we'll deal with this in two parts. We will first start by naming cations, and then anions, and then we'll put them together to form the names for ionic compounds. We'll start with cations. Cations actually are fairly simple to name. It's not too complicated. First, if the cation itself comes from a metal atom, then the cation will just have the same name as the metal itself. So sodium ion, zinc ion, aluminum ion. A slight complication to this is if the metal is able to form multiple different types of cations. So if you can have one metal that forms a 2+ or a 4+, or a 1+ or a 3+ cation, in that case, what we need to do is we need to specify which cation is being formed by putting a Roman numeral in parentheses following the name of the metal. Now, what metals do this? How would we know? It's primarily the transition metals, the ones in the middle of the table, that B block. The alkali metals in the first column, the alkaline earth metals in the second column, those only form one type of ion. But the transition metals are often able to form multiple types. And so the best rule of thumb is anytime you have a transition metal to automatically place the charge after the name of the metal. So an example here would be iron can form both a 2+ charge or a 3+ charge, and we would put iron 2 ion or iron 3 ion. And it does make a big difference because which cation is formed can have a big impact on the properties of the compound. For example, here are two different iron oxide compounds. The one on the left is an iron 2 compound, and the one on the right has an iron 3. So that's very important to keep track of that if we're dealing with transition metals. Lastly, there are some rare cases where we can form a cation from non-metal atoms. This is going to be what's known as a polyatomic ion. That means it's going to be an ion that's composed of multiple atoms. And there are two, and only two, that you will be required to know, and that is the ammonium ion and the hydronium ion. If we have a cation that's coming from nonmetals, we would put the ium or IUM ending before the ion. So these two are ones that you should know. Ammonium, and it's all one unit, it's NH4, 4 hydrogens bonded to 1 nitrogen as 1 unit with a positive charge overall, and hydronium as H3O plus on the whole unit. And then we can talk about just common cations here. And the ones that are highlighted in bold are ones that you really should be familiar with. You should memorize these. That way they can always be as a resource for you as you're solving problems or encountering objects on a test. And that's it for cations. So really fairly simple, not much complication there. The real challenge comes with anions because there's a large variety, but we'll start as simple as we can. If we have monatomic anions, that means just one atom with a negative charge, we name it by replacing the ending of the element name with the "ide" ending. So instead of it being hydrogen, it's just hydride ion. Instead of it being oxygen, it's oxide. Instead of nitrogen, it's nitride. If it was fluorine, it would be fluoride or bromide. In all of those cases, it's just one atom with a negative charge on it, and we replace the ending of the element name with "ide." There are a few polyatomic anions that also have names ending in "ide." So polyatomic again means that the anion itself has more than one atom involved, and it's a charge on the whole system. So hydroxide is probably the most common. It's an oxygen and a hydrogen bonded together, and the whole system has a negative charge. Cyanide or peroxide is another example here. Now, if a polyatomic anion contains oxygen, and it's not just like the peroxide. In that case, that would just be one element, just oxygen. But if it's multiple atoms of different elements in one polyatomic anion, and it contains oxygen, then the endings are going to be either ate or ite, and these are referred to as oxy anions. I'll give some examples here. So NO3- is the nitrate ion. And if we remove one oxygen from that, the charge does not change, but we now have the nitrite ion. So 8, that ending will always mean a larger number of oxygen atoms. The ite ending is always one less oxygen atom from the 8 ending. Sulfate and sulfite are similar examples. You will notice that the number of oxygen atoms present is not the same as the nitrate and nitrite ions, but that the ite ending ion is one less oxygen atom than the 8. I'll try to go through this in a little bit more detail. Things can get a little bit complicated. So normally there's just ate and ite for polyatomic anions, except for cases where the Oxy Anion series can extend to more members, such as 4. And this is primarily only for halogens, polyatomic anions that involve oxygen and halogens, such as chlorine, bromine, or iodine. So here, for example, we can have one series that, between chlorine and oxygen that can vary between 4 oxygen atoms all the way down to 1 oxygen atom. Notice that the charge does not change regardless of the number of oxygen atoms. But we can have, we add a prefix of per if we have 4, and we would have perchlorate. And then one less than that, the chlorate is just the common oxy anion, so it gets the 8 ending. One less than that is the ite ending, the chlorite, and if we remove another oxygen from that, we get the hypochlorite ion. There's a couple ways to look at this to help you remember what type of polyatomic anions there can be. In the second row, so period 2, where the elements are carbon, nitrogen, oxygen, fluorine, the maximum number of oxygens that you are allowed is 3. And the ion that has the maximum number of oxygens is going to be the 8 ion. So you have the carbonate and the nitrate ions here. If we removed one oxygen from NO3 to make it NO2, we have the nitrite ion. If we move down one row to period 3, then the maximum allowed number of oxygens is 4. And so for elements other than the halogens, the maximum number of oxygens becomes the normal 8 anion. And then one less from that would be the ite anion. The halogens form their own exception. Because they have all of those possibilities, the representative anion, polyatopic anion, is the one that has only 3 oxygens. Whether that's chlorine, bromine, or iodine, this is going to be the 8 ion. One more oxygen than that is going to be the per-8 ion. One less oxygen is going to be the ite, and one less oxygen than that is going to be the hypoite. And it could be hypochlorite if it's chlorine, or hypobromite if it's the bromine, or hypoiodite if it's iodine, and so forth. Now, let's take this a step further. If we have anions that are derived from adding an H+ to an oxy anion, Then we name that by adding the prefix hydrogen or dihydrogen in front of the anion name. So what's an example of this? What would this look like? We'll take the carbonate ion. It's CO3 2-. If we add an H plus to that, that reduces the charge by 1, and we end up with HCO3-. This is referred to then as the hydrogen carbonate ion. Or if you take phosphate and add 2 hydrogens, 2 H plus ions to that, you form the H2PO4-, and that would be the dihydrogen phosphate ion. So I know that the anion naming is a bit challenging. I highly recommend reading through the section in the book that details this process. Also, it might be helpful to make a sheet with common anions and cation names and how you go through the process of assigning the name, because it is absolutely crucial for you to be able to name ionic compounds. We must be able to understand what someone is talking about if they're talking about an ionic compound by its name. So as for the cations, we'll also list in your book, there are bolded anions. These are ones you should particularly pay attention to, although these are not the only anions that may show up. But these are ones that you should pay particular attention to. Okay, so we've gone through naming cations and naming anions. How do we put those two together? It's actually very simple. You take the cation name, you put the anion name in, and that's the name of your ionic compound. So here, for example, we have CaCl2. My cation is the calcium, so I would have a calcium ion. And the anion is going to be chlorine. We can look up the charge for that. That would be Cl-. And I've got a calcium 2+, a Cl-, so I bring those together. I bring those superscripts down to become the subscripts, and I come out with CaCl2. And in that case, then I have a calcium ion, I have a chloride ion, and so the compound name is simply calcium chloride. Another case here, aluminum nitrate. So we have an aluminum ion. It's not one of my transition metals, so it only forms one cationic charge. That happens to be +3 if we look at the periodic table. And then NO3, that would be the nitrate ion. We can look back at our list of polyatomic anions, so that's a nitrate. There are 3 of them because the nitrate ion itself has a -1 charge. Aluminum has a +3 charge. We take those 2 charges, make them the subscripts, and because it's the entire ion, because NO3 is one entire ion, I put parentheses around it, and then I put the subscript outside saying this is the number of that ion that are present. And that allows for charge balance. But I have an aluminum ion, that would be the name, and I have a nitrate ion, so it simply becomes aluminum nitrate. Copper perchlorate, we have a polyatomic perchlorate ion, and we have copper. Now, the perchlorate ion is -1 charge. I have 2 of them, so I would have a total of -2 charge. That means that the copper, which is a transition metal, so I don't necessarily know what it would form in terms of its positive charge normally, but the compound has to be charged balanced. So if I have a -2, copper must be +2. Because it's a transition metal ion, I need to put the charge in parentheses, and so it becomes copper 2 and then perchlorate. This last example here of cupric perchlorate, that simply has to do with the Latin name from this specific copper cation. You do not have to know that for naming ionic compounds.